In this video, what we're going to do is take the same concepts that we used in the last video, looking at energy balances for these discretized problems, and we're going to look at what's happening at the surface and really use that to investigate boundary conditions. So we'll do that looking at this section of the object. So we have an object here, which again, we've discretized by looking at, dividing it up into a grid, looking at the temperature at specific points. We can divide this up into control volumes like we did before, and specifically look at this one control volume that I'm shading right here. This is our control volume, Mn. And what we're going to do is look at an energy balance for that specific section of our object. That section of our object is at a constant temperature, Tmn, and it's experiencing conduction on three sides and convection with this fluid on the right-hand side at that surface. We're going to use the same idea, same equation for an energy balance that the change inside of that control volume is equal to the amount of thermal energy coming in. So we're going to have thermal energy coming in from all four sides. That equals the change in energy inside. So again, if 1 unit of energy came inside, the amount of energy inside would change by 1 unit. We have two different ways that energy can come into our object now. It can come in either by conduction. So if it's coming in by conduction, we could characterize that by the area over which conduction is happening, multiplied by the per area value of the conduction flux. So again, this area term is going to come up again. So the area times minus K delta T over delta X. So that would be conduction that's happening along the X direction. Or we could have something like this equation down below. So this is for our X direction, and this would be for our Y direction. So we could have conduction along either one of those directions, either X or Y. Those would be the equations. For convection, it looks basically the same, but now we have our convection model. So again, the area where we're experiencing convection multiplied by our convective flux, or again, to write it out, area times HC T infinity minus T. So this is our equation for convection. We have equations for conduction. Now let's do a heat balance for our specific control volume. So this shaded CV up here. We'll look at steady state. So d temperature dt equals 0 for steady state. And then that's going to be equal to the Q coming in at the bottom, or we'll do it this way rather. We'll look at first from the left plus Q from the bottom plus Q from the right side plus Q from the top. So this is our energy balance equation. The change in energy, or the change in stored energy, which is 0 for a steady state system, is equal to the energy coming in from each of these sides. Let's look more specifically at what that is. So the left-hand side, we're looking at the amount of energy coming in along this left-hand wall. It's coming into our object. That's coming in by convection or by conduction, right? So we have energy coming in that left-hand side by conduction. We can characterize that as conduction along the x-axis or along the x direction. The area that's happening over, that left side area, that is delta y. Okay, so we have the area that conduction is happening over, delta y, times our conduction model, minus K delta T. So that would be T TMN minus TMN minus 1 divided by delta X. The bottom is a little bit different. So the bottom, again, we have conduction happening here at the bottom here, but this area here is delta X over 2. Right? It's only half as wide there because we have the surface. Right? So a full delta X would actually take us like outside of the object to the right. So we only have a half of a delta X. So we'll put that in. So the area is delta X over 2. Now times our conduction model, minus K TMN minus T M minus 1N divided by delta Y. Now on the right-hand side, Q right, on the right-hand side, that's this wall here. Again, we have heat going into that wall, but this time it's going in by convection. So we have to switch models. We have to switch from our conduction model to our convection model. So this is A, which that area is delta Y, our vertical dimension, times HC T infinity minus T Mn. So that's the convection going into our system. Then the last term is what's happening at the top. So it's this top surface here, where again, heat is going in by conduction, but it's happening along a half width, delta X over 2. So this side is delta Y, this side is delta X over 2. Because that side's half as big. So this is plus delta X over 2 minus K TMN minus T should be M N plus 1 over delta Y. So this is now our energy balance equation. We can do a couple simplifications because if we choose a delta X which equals delta Y, then obviously delta X divided by delta Y equals 1, or vice versa. So anywhere we see a delta X over delta Y or delta Y over delta X, that's 1 because of how we chose the dimensions. We chose an evenly spaced grid. This gives us, okay, in this first term, we have a delta Y over delta X. So that will, again, just go to 1. The delta Y and the delta X are the same distance. So this is K Tm n minus 1 minus Tmn. Sorry, I should get my parentheses right. K times Tm n minus 1 minus Tmn. So I flipped that difference because of the negative that was on K. So I got rid of the negative, so I have a little bit easier time with it. But then I flipped my difference. This next term has a 1/2 out in front. 1/2 times K times T m minus 1 n minus T mn. My convection term doesn't have a delta Y over delta X. So it just has a delta y, so that stays there. So this is still delta y hc t infinity minus tmn. Nothing really changes there. And then this last term has a 1/2 delta x over delta y. So this is 1/2 k n plus 1 minus t mn. So we want to simplify this further. So we have a k out in front of 3 of the terms. So if we divide off by k, this will give us 0 equals tm n minus 1 minus tmn plus 1/2 tm minus 1n minus 1/2 tmn plus delta y hc over k t infinity minus delta y hc over k tmn plus 1/2 tm n plus 1 minus 1/2 tmn. All right, kind of a lot of terms, but let's look at exactly what this is. So let's get all of the tmn's over to one side, and let's let all the other stuff hang out on the other side. So this gives us, so tmn's, we have a 1 in front of it. Here we have a 1/2, 1 plus 1/2. Here we have this guy, so that's delta y hc over k. And here we have a 1/2 plus 1/2. So those are all our tmn coefficients. That equals tm n minus 1 plus 1/2 t m minus 1n plus 1/2 t m n plus 1 plus delta y hc over k t infinity. Okay, so we see kind of a cool thing actually happen. So this term, delta y hc over k, is the BO number, right? So BO equals HL over K. So this is really a BO number, which is describing right, how convection is happening. Right? The BO number looks at the ratio of convection to conduction to see which is faster or which wins, which weighs more. So we see this BO number crop up. And if we look at what our final solution is, if we solve for TMN, TMN equals TM n minus 1 plus 1/2 T m minus 1n plus 1/2 T m n plus 1 plus the BO number times T infinity all over 1 plus 1/2 plus 1/2 plus BO. And if you look at that, all that is a weighted average. TMN is is a weighted average of the surrounding temps. Okay, again, let's look back at our picture. So if you look at the top, how much of a factor is this top temperature that I've colored in red? Well, it's only connected by a half side length. So its weighting is only a half. This left temperature here, well, that's connected by a whole side. So that's weighting factor is 1. This bottom, well, that temperature here, that's only connected by a half side length. So that's weighting factor is 1/2. So that's exactly what we see. We see the weighting factor is 1 for the left side, and it's 1/2 for both the top and the bottom temperatures. Then the last temperature here, the last thing that's affecting it is what's happening on this right-hand side. So that's happening, well, what's the weighting factor? Well, it's the side length, which is a full delta Y, but we also have to take into account that this is convection and not conduction. So it's that full side length multiplied by the BO number. So the weighting factor is the side length times the BO number, so a whole BO number. So this is the temperature here, T infinity, and its weight is the BO number. And then, right, to take a weighted average, you simply, you have those weights associated with each of those temperatures, and then you divide by here the sum of your weighting coefficients. So our weighting coefficients are going to be the, for conduction, it's the side length. Or I guess the side length divided by delta X. For convection, it's the BO number divided by, it's the BO number. So like this would be 1 side length, maybe something like 1/2 side length. And this is, something like delta Y H over K, or it could be delta Y over 2 H over K. So it's it could be, if you have convection over only a half delta Y, for example, or a half delta X, you could have a 1/2 in front of that. But if you can picture this just as a weighted average, I think you can get a lot of just physical insight into how this is working. Where you have the temperature here of any one spot is related to, is a weighted average of the surrounding temperatures around that slice of space. Using this kind of, the same kind of idea, go through the next in-class assignment, and you'll be using the same concept to look at what are some possible other boundary conditions at different types of nodes, different types of exterior nodes. So you'll look through and hopefully get other types of boundary conditions. What are they? What are the simple equations for them? You don't have to go through this entire process, because kind of once you get the hang of it, you can just look at it and write down the equation without going through the whole derivation like I did here. But it might be helpful once to go through the derivation just to prove to yourself how this exactly works, how all of the things cancel out, and how all of the things fit together. But once you go through that once or maybe twice, hopefully you can start to pick out some of the patterns for these types of boundary conditions and how we can handle object surfaces.